This conference will now be recorded.
Okay. Good morning, everyone. Good afternoon from wherever you are joining us. Thanks for coming today. Today we have Dr. Jim Overland, who is a research oceanographer leading PMEL's Arctic Climate Dynamics Research Group, and he will be talking about supreme climate extremes today. This October, he's been working with NOAA for almost 50 years come October, and has been leading projects on jet stream dynamics, Arctic changes in historical climate and sea projection, and ecosystem impacts. And so with that, I'll turn it over to Jim.
Thanks, Ada. Well, normally when I've given talks here, they're generally downer overland talks that things are not going real well in the future, and I wouldn't want to disappoint people. So this continues in that frame, pointing out that things are not actually very good right now either. So the point today is, rather than looking at the climate models and average temperatures and going into the future, that looking at climate extremes that we're starting to see is a better way of really looking at global climate change. Next slide. So the traditional way of thinking about extremes is with a distribution that's the normal distribution or the Gaussian distribution, where you might have temperature increasing along the x-axis, and then the frequency of occurrence of a certain temperature on the y-axis. And so in setting up this, there are two parameters. One is the mean, which was the vertical bar, and then the standard deviation, which is a measure of the spread. The shape is always the same, but how far it spreads can vary. And so on the Gaussian model, 68% of all the observations will fall between plus or minus one standard deviation, and it's set up so that over 99% are within plus or minus three standard deviations. And you can do tricks with this model. What's shown in this example is if you increase the mean of the distribution, if you move the distribution so the mean is warmer, you pick up more extreme events down at the bottom. But what happens if you're out here beyond the end of the standard deviation? A lot of observations are that we're seeing now occur beyond what would fit to a normal distribution, and not only are they greater than observations that have been seen before, but often they're much greater than what have been seen before. And those observations are called radical uncertainty. I'm not sure that's the best phrase to use. I'd like to put something about climate in it. So I'm talking about super climate extremes, those that are beyond what have been observed by before. And these events, another name for them are black swans. That came up that in Britain all swans were white, and when they went to Australia there were black swans. So a black swan is an event that's well beyond and outside the range of thinking in terms of Gaussian model, and that bankers have made a lot of wrong decisions using the Gaussian model because it's so narrow for rare events, and they're not thinking outside the box in terms of what happens in the real world. And why would you think the processes that are defining the shape near the mean would be the same as those processes that are determining what are rare events? And that's the main problem with thinking in terms of a Gaussian model for extremes, that it assumes they're all caused by the same set of events, but in the real world you have new processes that kick in for extremes, and that's what I'm going to talk about. So next slide. So we've run into this on at PMEL in our fisheries oceanography, where we work with the fisheries service on what's happening up in the Bering Sea, and the loss of sea ice is one of the main processes going on. So the purple lines here are how far the sea ice has moved south during the winter in different years, and you see there's a fair amount of variability from year to year before 2014. But then in 2018, we had much lower sea ice, almost no sea ice in the Bering Sea that year, and it's really different than we've ever seen before. So it's one of these extreme rare events, and going back to, as far as they can see, took back to 1850. This has never occurred before, and it doesn't show up in the climate model forecast happening this early. And when we have these events, there are multiple causes that are interacting, and that's what makes it different from the Gaussian model too, that we have a wavy jet stream that relates to more southerly winds. You bring more warm temperatures further north, melts more ice, more open water for the ocean to observe, have more warmer temperatures. So that's what we've seen here, and not only was 2018 rare minimum, but 2019 followed on as a rare minimum. So if you thought one event was very rare. You've now got rare times another rare, and just what's happening there. And the sea ice really governs what happens to the ecosystem and the fisheries. And next slide. So the loss of ice really changed the whole ecosystem in the northern Bering Sea. And call it a reorganization, but the ice algae that use the ice as a platform, and when the ice melts, it starts the spring bloom and occurs early. There was no ice algae because there was no ice, and the ice, when it melts, causes a cold wall basically to keep the fish that are in the southern Bering Sea from moving north. And during 2018 and 19, pollock and Pacific cod, which are major predators, moved into the northern Bering Sea. And if you compare the number that they counted in 2019 compared to a more normal year in 2010, there were over 20 times the number of fish in the northern Bering Sea. And also Arctic cod, which is a fish that's normally found in the northern Bering Sea, were gone as well. And they probably moved north to stay in cold temperatures. So these were a heavy predation on the smaller fish and crab in the northern Bering Sea, which had a negative effect on the coastal communities in terms of their economics and food security. So that's one of the main things that FOSI PMEL is working on, and this is certainly the biggest event of my career that we're trying to keep track of. And if you remember on the sea ice figure, the ice did come back partly in 2022 and 23. So we don't have low ice every year continuing. So one of the main things we're working on is what's the chance of over the next 2 decades of continuing the low sea ice years, and then it propagates all the way through the ecosystem and people. So that's what really got us started on these extreme events. Next slide. One more closer to home here in Seattle was in 2001. There were wildfires and a heat wave in British Columbia, and the temperatures there were more than 6 degrees warmer than they had ever been before. And Seattle, they were about 4 degrees warmer than they'd ever been. And in the lower right here is a weather map of the winds halfway up in the atmosphere, where the winds follow those lines. And how this occurred was there was high pressure up in Alaska that propagated down over the Pacific Northwest, which was already had drought conditions. and then you set up with low pressure off of Japan, and then the high pressure in the Pacific Northwest, and then further downstream low pressure. And that's called a blocking weather pattern. So the winds are moving through there, but the shape of the pattern doesn't change. So for this event, you had prior drought, you locked in the high pressure that wasn't moving away. And then when you have high pressure, the air is sinking in the high pressure and it warms as it sinks. So again, you had three different factors that were adding together to give you this extreme, super extreme event over us. Next slide. Another example is a loss of snow melting on Greenland. That in 2022, the area of snow melt was more than twice that they ever seen before. And again, that's a positive feedback. The jet stream was oriented over Greenland. And then once you melt the snow, you can absorb more temperature at the surface rather than reflecting the sun off the snow. So another extreme that's well beyond what happened before. Next slide. So I put together a note to talk about these three examples, and we're going to see them before. And I turned that into the journal in early summer, and guess what? You kept seeing almost the newspaper every day had another one of these extreme events, and two that have come up was during summer there were wildfires in Canada almost the whole time, and if you have low pressure with counterclockwise winds over New England, it brings that smoke into the Midwest and then over Washington, D.C. The other one was when you had high pressure over New England, the wind goes the other way clockwise, and it came down the East Coast and hit New York City very, very bad. And you might remember they had severe air pollution, and no one could go out, and this was clearly a global warming event that had never happened before and got the attention of millions of people. The other one that happened last month is the ice is not refreezing very quickly around Antarctica, is shown in the right picture. So, and some of the foolishness on thinking in terms of Gaussian distribution. Someone has said that compared to the climatology in the last 30 years, that this was a 6 standard deviation event that was a once in 7 million year possibility. Well, it occurred and it was set up, and there are glaciers and interglaciers. Just comparing it to the last 30 years is not the way to think about it, but it's clearly a super climate extreme. And just this week, the news out of there is not good that a lot of the penguins that were on the Penguin Walk, if you remember that movie, perished because they didn't have their normal ice conditions. So when you have these physical events, there are downstream ecological events and affect people. So next slide. So rather than thinking about climate models that produce these kinds of projections for warmer temperatures in the future that are half a degree or something, or several degrees at the end of the century that really don't attract people's attention. I propose that a better way of thinking about global warming is pointing out that we have all these new extreme super climate events. Next slide. And thinking about how these occur, it's not just global warming by itself. It's the combination of climate change, global warming, that can be increased temperatures, droughts, loss of sea ice, melting permafrost, sort of ongoing thermodynamic changes, but then they hook up with the range of natural variability, and it's the two of these together that are producing these extreme events. And then you compare what's happening in the physics with the life history of the biology, and that ends up with ecosystem impact. So rather than thinking, oh, we have this gradual long-term warming, it's that the gradual warming interacts with these storms to produce these extremes, and that's what we're seeing. So next slide. So in summary, rather than just thinking radical uncertainty, black swans or super climate extremes, I think is a better way of thinking about it. And the characteristics on these is rather than just thinking of one cause like increased CO2, it's the combination of many processes adding together all at once that are creating these extremes. So they end up being regional, they can be of different types, they can be heat waves, sea ice going away, melting glaciers, wildfires. There's a lot of different types, but it's the local weather plus the climate change that's doing it. And so they're because they're related to the weather as well. They have a limited duration, and the question of what to do about them is a difficult question because you've never seen them before. So there's no analogs to look at. So we know there are going to be more events, but we don't know where or when or what type will occur. And so the best we can do is to define some worst case scenarios and think about how to plan for that and whether the worst case, is really going to be bad for a particular location. So I'll leave it there and open for any questions here or online.
People may be typing their questions online. Questions in the room?
So Jim, I'm trying to understand the concept of a climate extreme. So based on what you taught, it's still individual wiser extreme events under the changing climate.
Mhm.
So what's a climate extreme mean? Is that means so I'm still trying to understanding the concept here.
Yeah, I think the climate aspect of it is you don't think of just one event, you think of a whole series of these events occurring. And so the background conditions that you're living under are different than they were before. So, and it's the combination of weather plus the longer term thermodynamic changes that are doing it. So there might be a better way of saying it, but I think having climate in there is the idea that we're really shifting something. And it's not just the mean temperature, it's the occurrence of these extreme events. It's more about the frequency of the events.
I got one. So first of all, thank you, Jim, for that presentation. It's sobering stuff for sure. My question for you is, so given how radically things are changing and the radical nature of these events, what are the research needs? How are the research questions changing, and how are the research needs evolving? And what do you see as the big questions that we need to now turn to in order to better understand and predict these types of things?
Well, the first research need is to catalog all these events so that we know the type and can we say something about how they're put together. As I put out, we don't know where or when they occur, but once they occur, we can actually put a story together on what was the combination of individual factors that added it together. So the first one is to understand what there is, and the next one, and we're doing that for the Bering Sea, is can we say anything about what's the frequency that these might occur? And we can use models, we can go back and look at, even though we didn't have the extreme sea ice in the past, we've had weather events that have been similar. So we can see how those come in. And so our preliminary look at that is we have one or two of these southerly wind events every decade in the last 5 decades. So looking for the 2 decades forward, we can say right now that they're not going to happen every year. And we might have between 2 and 4 in the next 20 years. So that's the other half of looking at the research.
Jim, you have a question online. So going back to the first slide, let me go back to the first slide. Al, tell me if this is the slide you meant or if it's the next one. Another way?
That's the one there.
Perfect. Do you want to ask your question since you're already on mute?
Okay, yeah, yeah, going back to this slide is another way of describing what's happening to say it's not just the distribution is shifting to a different mean, but it's also spreading. I mean, you could still say this kind of normal distribution way of looking at things is valid, but it's just the variance is changing as well as the mean.
But my point is that it's beyond just the standard shape of the Gaussian, describing some of these radical uncertainty or the extreme events are actually long tail events, if you want to think in terms of this. It's not a Gaussian, but the tail to capture them would be a different function than the Gaussian model. I think that was my main point there.
So you're saying the physical system is no longer going to have a Gaussian distribution. It's going to have, well, I guess.
Yeah, and what, why would you think that the processes that are causing the events around the mean are going to be the same as what would happen out on the tail? And in the examples I showed, when you have these multiple causes, that would be another way of thinking that the Gaussian would be more single or a few causes where what we see on the broad tails now are really multiple interacting processes that are causing the extremes.
Okay, one more question online. Allison asks, once you have an extreme event, you can imagine that event recurring, but how do you think about events that have not happened? How do you plan for those?
Yeah, that's the big question here. Rather than just running climate models and saying they're going to give us the answer, you have this fundamental philosophical question about how you deal with something you've never seen before. And the people that worry about that are thinking in terms of scenarios that, what can you imagine as being nearly a worst case? And is the worst case going to be catastrophic or not? Maybe it's not going to be catastrophic and you're going to be okay, but envisioning scenarios is how people are approaching that.
Yeah. Al added that it sounds like unknown unknowns. Okay, any other last call for questions, either in the chat, you can come off mute and ask them, or in the room.
Yeah.
Can you talk a little bit about current or emerging technology that would help improve a model or detect an extreme weather event?
Well, the climate, the weather models are improving because they're they're getting better at absorbing the satellite picture. So last year there was a major late summer storm in Alaska that flooded everything. But they know that it was a typhoon that picked up more energy during warm sea surface temperatures in the North Pacific. So, so overall, they're getting better at that. But again, it's, how do you think about something that never happened before? And so the idea is, if you're concerned about it, what can you imagine, and then how would you respond to that? So, the issue of preparedness is important. So, what do you do about flooding and planning for floods? We have a lot more wildfires, and better planning for how you deal with them. So the technology is improving for looking at those, but there's very little we can do to really stop them. I think we're going to have more and more in the next decades.
Thank you.
Another question online about what use are any of the previous climatologies used to compare to what's happening now?
Can you put the next to the last slide up? How I've come to think about it is you have climate change going on, which is the background long-term changes. But when we have these, we have the natural variability of the storms that are mixing with the climate change pieces. And so this is the real hopeful part, is we have 50 years of good weather data looking at the natural variability of the storm events. So for instance, as I mentioned, for the low sea ice in the Bering Sea, that goes with southerly winds, which goes with the Aleutian Low being far to the west. And so we can go in the 70-year record and say how often is the Aleutian Low far to the west, and that's once or twice a decade. And so we can use that going forward as our analog. It's not all new. The weather part on this conceptual model is available.
What's going on in the Antarctic with the sea ice extent? Any ideas what's going on there?
For 50 years, I said I don't look at the Antarctic. I haven't gone all the way through, but clearly it's warm temperatures, the change in the winds, and the change in the currents that are related to that. And it's not only the sea ice forming, but it's the melting of the glaciers, and that they may start calving again. So certainly it's a place to look at, but this extreme event this summer in Antarctica, if you look at that curve, it actually starts during their summer and it's continued all year. So it's a major event. And while I made a joke about the once in 7 million, certainly the whole Antarctic community is looking in detail that this is a super climate extreme.
Okay, second last call for questions. I don't see any more online, but we'll give it a minute.
I'll ask one more
Yeah, there you go.
from afar. I'm just thinking still about the statistics, and if you're saying things are becoming perhaps less Gaussian, maybe it's a matter of the central limit theorem says if you've got a bunch of things that are non-Gaussian, you add them together, they still tend towards a Gaussian if you're just adding them together. Maybe if the system is rearranging to become more multiplicative, so that the end result is rather than a sum of individual things, a bunch of things interacting strongly with one another, perhaps it then becomes more log normal rather than normal.
Yeah, that's a good point. But again, the central limit theorem is looking at things towards the middle of the distribution, not out at the far extremes. And so, I'm not ready to say that, we can fit any kind of long tail distribution out there and know and think that that's how the real world works.
Okay. Now, who wants the question? Okay, well, thank you, Jim. We'll give you another. I hope that I'll wrap up. I don't know. I'm just gonna stop the recording and then we'll hopefully have this up online in, I don't know, a couple weeks or so on YouTube. And then if you have any questions, feel free to contact me and I can give you Jim's email. So thanks, everyone.
Thank you.